All right, we've dealt with inverse sine and inverse cosine, so it's time to deal with inverse tangent. By way of a reminder, the inverse tangent goes from negative pi over 2 to pi over 2, but it behaves asymptotically. Now, this is just one cycle. This is my canonical cycle, if you will, of tangent. And let's see, I'm just going to kind of estimate it here. Remember that these are asymptotic curves, so this curve here will never touch the line x equals pi over 2 or x equals negative pi over 2. Now, we also have asymptotes farther along and farther back, and we have cycles of tangent in those areas as well. But for our purposes today, we're just going to be dealing with this one cycle in the same way as I drew one cycle of sine and then reminded you that it went on, right? It had additional hills and valleys beyond the canonical cycle that we sketched, and the same thing with cotangent. I sketched the canonical cycle of cosine, and then I reminded you that it went on, but we were really only interested, at least at first, in that one full cycle. So we're going to look at one full cycle of tangent. Notice that, now that I've said that, I'm going to go back and look at the whole thing. Notice that if I graph a vertical line anywhere through this graph, through the graph of tangent here, the graph passes the vertical line test, but it would not pass the horizontal line test. Let me throw a horizontal line in there, I think. All right, it goes through tangent here, it goes through tangent here, this horizontal line goes through tangent here. So if I try to use multiple cycles, then my arctangent, my tangent inverse, is not going to be a function. Now that was true of sine and cosine as well, which is why we started by paring down the graph to just one cycle. And then we looked at one cycle and found that even within that one cycle, that was too much, that just that one cycle would fail the horizontal line test. So now we're going to do the same thing with tangent. Looking just at this cycle here, we can see that if I drew a horizontal line anywhere, this one cycle, this one curve here, will pass the horizontal line test. So I don't need to further restrict my domain for tangent in this case. I do need to restrict it to one cycle, but that's all I need to do. So now let's use this information to graph tangent inverse. Now, because the roles of x and y reverse when you are dealing with an inverse, I'm going to label my x-axis. Actually, I don't think I'm going to bother to label my x-axis. I'll put a couple of tick marks in here because I see the y values here go from negative infinity to positive infinity. So when I graph my inverse, the x values are going to go from negative infinity to positive infinity. The x values on tangent, on the other hand, I have to restrict because I want it to pass the horizontal line test, and it only does that for one cycle at a time. I'm going to have to restrict my x values to as the distance that it takes to make one cycle, and that's negative pi over 2 to pi over 2. So that means over here, I'm going to restrict my range from negative pi over 2 to pi over 2. We didn't spend a lot of time graphing tangent very accurately, so let's go back in now just for a moment and remind ourselves that at pi over 4, the tangent has a value of 1. So on my graph, this point right here should be 1. And at negative pi over 4, I'm at negative 1. So right here, negative pi over 4, this value right here should be negative 1. All right, so now I have several points on my tangent graph that I can use to graph my cotangent graph. Actually, it's going to go this way. So let's plot those points. I have 0, 0. That's an easy one. The roles are reversed, but the values are the same. And then I have pi over 4, 1. So I'm going to have 1. Let's make this 1 and this negative 1. And that's going to be negative and positive pi over 4. So where I had on my tangent graph where I had pi over 4, 1, I'm now going to have 1 pi over 4. So I have a point there. Equally, based on my point for tangent at negative pi over 4, negative 1, I will have a point on my tangent inverse graph at negative 1, negative pi over 4. So I have a point there. Where I used to have vertical asymptotes, I now have horizontal asymptotes. Sketch those in a little bit. And then noticing that this curve goes sort of towards the first asymptote first before it goes up, I'll make that observation here as well. It goes sort of towards the first asymptote. So it's going to look something like this, and that's the way it curves. Now this one's a little bit less difficult to guess how it's going to. So we have for tangent that if we want to be allowed to play around with inverse tangent, we have to restrict the domain of tangent from negative pi over 2 to pi over 2. But there's something else we have to be careful about here. I've written this in exactly the same way as I would have written the restrictions on the domain for sine, but it's not accurate. It's not right at this point, because you'll notice here that this tangent curve never touches this asymptote of pi over 2. So actually, it's not or equal to. It's just strictly less than. Negative pi over 2 is strictly less than x, which is strictly less than pi over 2. And of course, I can write that in interval notation just using parentheses instead of square brackets. Okay, let's take a look at a couple of examples. If I'm asked to evaluate an arctangent, or the arctangent of a value, then I'm looking for the angle, let me write this as equals theta. Now, my angles at the moment are let's see, where am I? My angles are x's, right? I've been talking about the tangent of x and the arctangent of x, but I'm using theta here just to help clarify what's going on. Then I have a couple of options here. I can go figure out what the arctangent is of 1 over the square root of 3 and then figure out what quadrant I'm in. Or I can read this value off of a table and then figure out what the arctangent is, what the angle is that gives me that value in the table. Let's take a look at it analytically. Remember that tangent is opposite over adjacent. So there are two places where I might have an opposite over adjacent that's negative. If I have an, let's see, an opposite here, which is positive, or over an adjacent that's negative, I could be in quadrant 2, and that would give me a negative tangent value. Or I could be in quadrant 4, where my opposite would be negative, but my adjacent would be positive. So that would give me a negative tangent value also. The thing is, we are only allowed to play with arctangent in quadrants 4 and 1, much like sine. The difference here is I can't let my angle be either negative pi over 2 or pi over 2, so I can't go all the way out to the extremes, but everything between those two values. So that tells me that I am not going to be using the angle in quadrant 2. I'm going to be using the angle in quadrant 4 to answer this question. So I have to figure out, first of all, what the angle is whose tangent is 1 over root 3. And then from there, I can figure out what that angle actually is. This is the reference angle, and I'll be saying that my answer is negative that number, negative that angle. And the answer is, the angle that I need there, the arctangent of just positive 1 over root 3, it's my reference angle, that's pi over 6. But that's in quadrant 1, and I need to be in quadrant 4. So if my reference angle is pi over 6, then this angle right here, this little angle that's back from 0, the size of that angle is pi over 6. That's the size of that angle. And I have a couple of different ways of thinking about that angle. I can think about it as this is 6 pi over 6. This is 2 pi or 12 pi over 6. So this would be 11 pi over 6. So the answer to this is 11 pi over 6. Don't write that down because it's actually wrong. I'll come back and explain why in a second. 12 pi over 6 minus 1 pi over 6 is 11 pi over 6. The other way I can think about this is as negative pi over 6. That's equivalent to negative pi over 6. But it's not the same as 11 pi over 6. So how do you know which one is right? Well, let's go back up to here and remind ourselves that the domain that we're allowed to play with is negative pi over 2 to pi over 2. Negative pi over 2 is pi over 2 below or back from 0, and positive pi over 2 is pi over 2 around, or I don't know how to say this, it's a positive angle, right? Pi over 2 is a positive angle. If you go in a positive counterclockwise direction, negative pi over 2 is in a negative or clockwise direction. So my angle has to be somewhere not between pi over 2 or 3 pi over 2 and 2 pi, but between pi over 2 or negative pi over 2 and 0, or negative pi over 2 and positive pi over 2. So that's why the negative pi over 6 is the correct answer here. Get the color of the highlighter that I want. This is the correct answer. 11 pi over 6 is not the correct answer because it's not in this range of values. It's not between negative pi over 2 and pi over 2. It's a lot bigger than pi over 2. Okay, it's time for our examples. As usual, I'm going to start with this one. I want to take the tangent of this angle and then take the tan inverse of the value that I get in there to get the answer. And the answer is simply negative 22 over 21 pi, as long as this value here is somewhere between negative pi over 2 and pi over 2. Is negative 22 over 21 pi somewhere between negative pi over 2 and pi over 2? It is not. I can test this by setting up an inequality. Negative pi over 2 is less than negative, I'm going to leave myself some space here actually. This is what I want to be true. Negative pi over 2 is less than negative 20, what was it? 22 over 21 pi, 22 over 21 times pi is less than positive pi over 2. And if this is true, then I can multiply this fraction by 21 over 21, and this fraction by 21 over 21, and this fraction by 2 over 2, and I'll get, I don't have enough room here really, I'll get negative 21 pi over 42 is less than negative 44 pi over 42, which is less than positive 21 pi over 42. Well, this part's true, right? Any negative number is going to be bigger than any positive number. So that part is true. That inequality is true. But looking at this part, this negative number is not, in fact, smaller than this negative number. This number here, the absolute value of this number is greater than the absolute value of this number. But for that very reason, because they're both negative, this number is actually bigger than this number. So this inequality, this part of my inequality, is not true. Therefore, the thing I wanted to be true is not true. And therefore, the angle I was looking for, negative 22 pi over 21, is not between negative pi over 2 and pi over 2. So I can't just say this. This is not the correct answer. What I need to do instead is figure out where this angle is, and let's just go ahead and do that part first. Where is negative 22 21st pi? Well, the first hint here is that I'm moving in the negative direction, right? This is a negative angle, so I'm going to go clockwise around my circle. If I go 21 21/21 pi, I get to here. An additional negative 1 over 22 pi puts me just into quadrant 2. So I can take the tangent of this angle, or I can take the tangent of this angle, or I can take the tangent of just this small angle and then just check the sine, S-I-G-N. Let's do that. The opposite over adjacent here is going to be negative. So when I take the tangent, I'm doing the inside first here. I'm taking the tangent of this angle here. I'm going to have the tangent inverse of, and then the tangent of this angle is going to be negative. And once I know that, I can take the tangent just of the reference angle. So now what I'm doing is figuring out what the tangent of this angle is. Well, this angle here, notice I'm talking about this the small angle here. I want to know what the size of that angle is. I'm not talking about this angle here. I'm talking about the reference angle here. And that was 1 over 21 pi. It was one more than 21 over 21 times pi, right? Just pi is 21 over 21 pi. This was one more than that when we went in this direction. So the size of this angle is 1 over 21 pi, or pi over 21. So if I take the tangent of this larger negative angle, I'm going to get negative the tangent of the reference angle. Well, now I have a new problem, because what I wanted to get was tangent inverse of tangent of a smaller angle, and then I could just say the answer was pi over 21. But I can't do that because of this negative in front here. My formula, let me write it up here in the corner, says that the tangent inverse of tangent of x equals x if x is in, I'll write it this way, the range of values negative pi over 2 to pi over 2, not including those two actual endpoint values there. And my formula doesn't include a negative here, right? So I can't use that. But what I can use is the graph of tangent to say, well, what is the tangent of a small positive angle look like? The tangent of a small positive angle is a small positive value. If I take the opposite of that, here, let me do it this way. My y value here would be about there. I'm just taking a generic kind of random small angle value like that. It's actually too big for our purposes, but it's in the right sort of arena. That's a small positive angle, and it has a small positive tangent. So if I want a negative tangent, a small negative tangent, then I'm going to need to come down here into the negative y world, and that's going to spit out, or it's going to come from a small negative. Ultimately, what I'm getting at is that tangent is an odd function. And remember that the definition of an odd function is that, let's see, I'll put it in this box here. A function evaluated at negative x is equal to the opposite of f of x. So I can rewrite this down here as the tangent inverse of the tangent of negative pi over 21. Put my 1 in the wrong place there. 21. There we go. And therefore, my answer is, now it's in the right form. Now I have the tangent inverse of the tangent of an angle. And I know my angles between negative pi over 2 and pi over 2. And therefore, my answer is just negative pi over 21. Okay, now we've left this example till last. So I'm going to erase. Do I want to erase? Yes, I think I want to erase this graph. So I have a little bit of space here. It's not going to take me very long, and it's not going to take me much space to do this. My initial reaction is to say that the tangent of the tangent inverse of negative 1 is negative 1. And that's a good gut reaction, but I have to check and see whether I'm allowed to use that value here. Here's my definition. Actually, this is not quite the same definition. And if you'll remember from sine and cosine, we had different ranges or different domain restrictions we had to use on this order, tan inverse of tangent, than we did. Let me go back. We had to use a different domain restriction for sine inverse of sine than we did for sine of sine inverse. We had a different domain restriction for cosine inverse of cosine than we did for cosine of cosine inverse. So the question is, do we have different domain restrictions for tan inverse of tan than we do for the tangent of tangent inverse? And the answer is yes. Just like sine and cosine, we have different domain restrictions, or different domains, I'll put it that way. Let's take a look at the domain and range of tangent. The domain is all real numbers except for pi over 2, and let me write this out because this is going to come up again in the future. Pi over 2 plus any integer multiple of pi more or less than that. what that means is that pi over 2 is not a valid input for tangent of x, right? It's an asymptote there. But the next one that's not a valid input for tangent of x is not the next pi over 2. That would put us at pi, and that one's okay. It's the next one beyond that. So starting at pi over 2, I have to add a whole pi before I get to the next asymptote. So if k is an integer, we would write that like this. If k is an integer, and that's 1, 2, 3, 0, -1, -2, and so on, then multiplying pi by integers gives me the 0th instance of this, so pi over 2 plus 0 times pi. The next one is pi over 2 plus 1 times pi. The next one's pi over 2 plus 2 times pi, and so on. Down here, I have negative pi over 2, so this is pi over 2 plus -1 times pi. This is still a pi-wide range of values. So starting at pi over 2, add -1 times pi, -2 times pi, and so on. So this is how you can write the values of all the asymptotes, or all the values that are not allowed to be plugged into pi. All right, that was a bit of a diversion there. So my question was, what is the domain of tangent? It's all real numbers except for these ones, pi over 2, and then multiples of pi beyond that, right? Almost all real numbers. The domain is almost all real numbers. The range is all real numbers, right? It goes from -infinity to +infinity. It does that multiple times. Tangent does. We're only looking at this particular cycle right now, but the range is all real numbers, however you slice it. That means that what did I say domain here? The range is all real numbers. For tangent inverse, therefore, the domain is all real numbers. So for tangent inverse, the domain is all real numbers. I'm not actually restricted at all. When I take the tangent of a tangent inverse, this is going to give me an angle, right? And then I'm going to take the tangent of that angle, and the tangent of the tangent inverse is the tangent of the tangent inverse of x is just x. As long as that x is in the restricted domain. Well, the domain isn't restricted in this case. In this order, tan of tan inverse, my domain is not restricted. So here's my answer. That one wasn't too bad. I'm not going to take the time to talk about calculator work on this one either, because again, all you have to do to find the tangent inverse of some decimal is to type second tan inverse, type in your number, and hit enter. I'm really not interested in whether you can use a calculator. Most people know how to use a calculator, or you can figure it out. I'm much more interested in whether you know how to think about the mathematics. Yes, there will be times when a calculator will be necessary and very handy, but by and large, I'm not terribly worried about that. All right, now in the next video, we're going to talk more about inverse trigonometric functions, but we're going to put them all together. All that's left is cotangent, secant, and cosecant. So we'll put those all together in one last video for this section.